Dear students, now we are going to discuss balanced modulator and ring modulator for generation of DSB-SC AM waves. In double sideband suppressed carrier method, the modulated wave consists of only the sidebands, that is, both upper and lower sidebands. Here, the carrier signal is suppressed in order to increase the transmission efficiency. There are two ways of generating the DSB-SC waves. One is balanced modulator, the next one is ring modulator. In this video lecture, I am going to explain balanced modulator and ring modulator in detail. Let's start with balanced modulator. This is the block diagram of balanced modulator, the circuit diagram. Here we are going to use two nonlinear devices in order to suppress the carrier wave. Here we have to consider the semiconductor transistors as a nonlinear devices. These two transistors are connected in a balanced mode. That's why it is called as a balanced modulator. Okay, so here we have to assume two important things. One is these two modulators should be an identical one and the entire circuit is a symmetrical circuit. The modulating signal is given as an input to the base of both the transistors. For this T1, the modulating signal is given as such, like M of T. For this second transistor, the message signal is given as minus M of T because we are giving the input signal through the lower portion of the transformer. Okay, so it is the minus M of T. The carrier signal is given to both the transistor as such. Is that okay? So here we are going to use the non-linearity property of the transistors to suppress the carrier wave. In this circuit, the input voltage to the transistor 1 is VBE1. Input voltage to the transistor 2 is VBE2. This VBE1 is nothing but the addition of M of T and C of T. Likewise, VBE2 is equal to minus M of T and C of T. So these two are the inputs given to T1 and T2. The output voltage is approximately equal to the difference between the output currents of T1 and T2. Here IC1 is the output collector current for this transistor T1. IC2 is the output collector current for this transistor T2. The difference between these two currents is approximately equal to the output voltage. These currents are depending on the nonlinearity property of the transistors. Let's see in the analysis part in detail. In order to suppress the carrier wave, two nonlinear devices are connected in the balanced mode. Here we have to make two important assumptions. One is identical transistors and symmetrical circuit. The input voltage applied to the base of transistor 1 is VBE1 of T. It is the sum of modulating signal and the carrier signal. So here M of T plus C of T. The collector current of the transistor depends on the nonlinearity property of the transistor. What is the nonlinearity property of the transistor means? The current is equal to the output current, that is collector current is equal to A into input voltage plus B into input voltage squared. So this is the non-linearity property of the transistor. Here we are going to use this property. So here collector current IC1 is equal to A into VBE1 of T plus B into VBE1 squared of T. A and B both are constants. VBE1 of T is nothing but M of T and C of T. So here we are going to substitute this expression. So we can get IC1 is equal to A into M of t plus C of t plus B into M of t plus C of t the whole square. Okay, so in the next step we are going to multiply the constants inside the expression. So we can get A M of t plus A C of t plus, here it is in the form of A plus B the whole square. So we can expand the formula as A squared plus B squared plus 2AB. So we can get B into M squared of t plus B into C squared of t plus 2B M of t into C of t. As we know that the message signal is given as Vm cos omega mt. Here Vm is nothing but the amplitude of the modulating signal. Omega m is the angular frequency of the message signal. C of t is equal to Vc cos omega ct. Vc means amplitude of the carrier signal. Omega c means angular frequency of the carrier signal. So we are going to substitute these two values in the above expression. Then we can get IC1 is equal to A M of t is replaced as Vm cos omega mt plus A C of t is replaced with Vc cos omega ct plus here B into Vm squared cos squared omega mt plus B Vc squared cos squared omega ct plus 2B Vm Vc cos omega ct into cos omega mt. Consider this as the first equation. So this is the output current from the first transistor. Okay. So next, the input voltage applied to the base of second transistor is VBE2 of t. So again we are going to add the modulating signal and carrier signal. For this transistor 2, the modulating signal value is minus m of t. So here we are going to add minus m of t and c of t. So we can get the answer as minus m of t plus c of t as the input voltage to the second transistor. The collector current of second transistor is IC2, that is equal to, again the nonlinearity property here, A into VBE2 of t plus B into VBE2 of 2 squared of t. Okay. So here we have to substitute that VBE2 of t as C of t minus M of t. So we can get like this. Okay. So A into C of t minus M of t plus B into C of t minus M of t the whole square. So here it is in the form of A minus B the whole square. So we have to expand like A squared plus B squared minus 2AB. So we can write A into C of t minus A into M of t plus B into C squared of t plus B into M squared of t minus 2B M of t into C of t. After that we have to substitute the value of M of t as Vm cos omega mt, C of t as Vc cos omega c of t. So likewise we can expand the expression like this. So now we can obtain the collector current of the second transistor IC2 as A Vc cos omega ct minus A Vm cos omega mt plus B Vc squared cos omega squared t plus B Vm cos squared omega ct minus 2B Vm Vc cos omega m cos omega ct. Okay, so consider this as the second equation. The output voltage of the balanced modulator is given like this. The output voltage V0 is directly proportional to the difference between the currents of T1 and T2. So V0 is directly proportional to IC1 minus IC2. So here IC1 and IC2 both are flowing in the opposite direction in the tuned circuit. So that's why we have to consider the difference between these two. Then we have to equate that equation. Then we can get V0 is equal to K into IC1 minus IC2. Okay. So here K is a constant. It depends on the impedance and circuit parameters of the balanced modulator. Okay. So next we are going to substitute the first two equations. We have found the value of IC1 and IC2, right? So we have to substitute the expressions of IC1 and IC2 into this equation. So substitute first and second equation in this third equation. So we can get V naught of t is equal to K into, so this is what the, what is this? This is what the, yes, IC1. Here it is IC2. So A Vm cos omega mt and plus A Vc cos omega ct plus B Vm squared cos squared omega mt plus B Vc squared cos squared omega t plus 2bb. So this all are the IC1 minus, this is the formula, right? IC1 minus IC2. So minus, this is what the IC2 expression. A into Vc cos omega ct minus A Vm cos omega mt plus as such. Okay. So then we have to multiply this minus inside to all the terms here for this IC2. So this term is nothing but IC1. This term is nothing but IC2. Okay. So multiply this minus inside this expression, you can get like this. So A Vm cos omega mt plus A Vc cos omega ct plus B Vm squared cos squared omega mt plus B Vc squared. This is what the normal IC1. This all are the minus IC2. Okay. So now we can cancel the similar terms. This one and this. Okay. So we have to cancel the similar terms. Okay. Plus and minus cancel each other. Then we can get A Vm cos omega mt here plus A Vm cos omega mt. So we can get 2 into A Vm cos omega mt. Okay. So the next, okay, here it is 2b Vm Vc cos omega mt cos omega ct. Here again 2b Vm Vc cos omega m cos omega ct. So 2 plus 2 4 plus 4 this term. Okay. Finally, we can get the output voltage V naught of t is equal to K into 2A Vm cos omega mt, that is nothing but the modulating signal, that is original signal, plus 4B Vc Vm cos omega mt into cos omega ct. So this is nothing but the double side bands. Okay, there is no carrier signal. Okay, so this is what double side band suppressed carrier output wave. Okay, so further it can be simplified as 2K. We can take this Vm outside, so both are having the 2Vm, and we can take the A value also. So here we can take that A here. So we can write 2kVm A. It is not A1. It is simply A. Okay. A into 1 plus, because we have to take this omega mt also outside as a common. So this term becomes 1. So 2kVm A cos omega mt into 1 plus 2b Vc by A cos omega ct. Okay. So next we can write this term as a modulation index of the modulator, balanced modulator. So here we can mention this as 2kA1Vm into 1 plus MA cos omega ct into cos omega mt. Okay. So this MA is nothing but modulation index of the balanced modulator. This is the output of the double sideband suppressed carrier using balanced modulator. So next one is ring modulator. Ring modulator is also called as diode balanced modulator. So in this modulator we are going to use diode as a non-linear device. Hence it is called as diode balanced modulator. Here we are going to connect 4 diodes in a ring formation. Hence it is called as ring modulator. The input and output side 2 transformers are used. It is represented as input transformer and output transformer. The modulating signal is given to the input transformer, and we can take the output from the secondary winding of the output transformer. Carrier signal is applied to the center taps of both the transformers. Here the 4 diodes D1, D2, D3, D4 are connected in ring shape. The modulating signal M of t is applied to the input of input transformer. The carrier signal is applied to the center taps of 2 transformers. Here the carrier signal is acting as a switching signal. For better understanding of the carrier suppression technique in ring modulator, we have to assume that the modulating input signal is 0. Only the carrier signal is present. So here we have to assume there is no modulating signal. Only the carrier signal is applied to the center taps of the transformers. So in this case, during the positive half cycle, diodes D1 and D2 both are forward biased and D3, D4 are reverse biased. So forward biased means it can conduct the current, reversed biased means it doesn't conduct the current. That's why we mentioned with the dotted line. There is no current conduction. It is in off condition. Okay. So during this positive half cycle, the output current divides equally in the primary winding of the output transformer. So equally divides in the opposite direction. Since it is in the opposite direction, the magnetic fields cancel each other. Therefore, there is no output signal. Similarly, during the negative half cycle, D1 and D2 both are reverse biased, D3, D4 are forward biased. At that time also, the current is equally divided between upper and lower portion of the transformer, and again both the magnetic fields are in opposite direction, they can cancel each other. There is no carrier signal at the output side. So thereby we can suppress the carrier signal in this modulator. Do you all understand that? Okay, so that's what given here. The output current divides equally in the upper and lower portions of the primary winding of output transformer. The magnetic fields cancel each other since it is in opposite direction, and there is no output induced in the secondary winding of the output transformer. Thus the carrier is effectively suppressed. So next we have to consider the scenario both modulating signal and carrier signals are present. So in this case, the modulating signal M of t is applied to the primary of input transformer and will also appear across the secondary winding of the input transformer. So whatever we are giving at the primary winding, the same will be available in the secondary winding in the input side. This is the M of t is given over here, right? So during the positive half cycle of the carrier signal, D1 and D2 both are forward biased and conduct the signal. So at the time D1 here, this is D1, this is D2, both are in forward bias. It can conduct the current, and then the same amount of signal is present at the output transformer side. Okay, so that's what given over here. During the positive half cycle, D1, D2 are forward biased and conduct the signal. As a result, the modulating signal is given to the primary of output transformer through D1 and D2. During the negative half cycle, D3 and D4 are forward biased and they will connect to the input transformer and output transformer with reverse connection. So this reverse connection reverts the polarity of modulating signal. That is called as phase reversal. Okay, so during the negative half cycle, it reverts because we are applying or we are giving the carrier signal at the center taps, right? At the center taps of the transformer. So it can reverse the phase of the modulating signal. So when polarity of the modulating signal changes, the 180-degree phase reversal occurs in the double sideband suppressed carrier wave. Signal representation of ring modulator method. This is the modulating signal, that is the original signal or baseband signal given to the input transformer, and here it is the carrier signal C of t. So in the primary winding of the output transformer, we can get the double sideband suppressed carrier wave like this. Okay, so here during the positive half cycle of the carrier, diode D1 and D2 both are in forward biased and it starts conducting the current. So at that time it starts conducting. Okay, it starts D1 and D2 both start conducting the current. Okay, during the negative half cycle, D3 and D4, correct, D3 and D4, these two are in forward biased condition. At that time D3 and D4 start conducting the current. Okay. Likewise, the next positive half cycle D1 and D2 conduct. So we can get the signal like that. Next negative half cycle D3, D4 conduct. So we can get the signal till this point. Okay. So whenever the modulating signal changes. Okay. So whenever the modulating signal changes to negative half cycle along with the carrier signal, here the carrier signal acting as a switching element, and it can switch the or revert the polarities of the modulating signal. So here it reverts the polarity of the modulated signal. This is called phase reversal. So here at this point, whenever here we are having the negative half cycle of the modulating signal along with the carrier signal, we can get the phase reversal like this. Okay, so at that time, okay, so entirely it is changed. During the negative half cycle of the modulating, at that time D1 and D2, these two are forward bias during the negative cycle of carrier signal. Okay, so this is the point over here. You can see here it is D1, T2 conduct during positive half cycle of modulating signal. This here D1, D2 conduct during the negative half cycle of the modulating signal. Okay, this changes happens because of this carrier signal. Okay, so here this is the primary winding output. In the secondary winding, this is the actual output. Okay, this is the actual output from the output transformer. This is the double sideband suppressed carrier signal. Okay, so here you can see the relation.